Let's make a start. So yesterday we looked at a phenomenological model of early dark energy. The idea was to have an energy injection into the cosmic fluid that reduces the sound horizon and is then compensated by raising H0, which is what we need to address the Hubble tension, right? So, and we wanted to approach the idea of early dark energy in a model independent way, at least as far as that is possible. So what we set up is an effective fluid model where we said that at an early stage, we have a fluid that behaves like a cosmological constant. So it has an equation of state of -1. But then, as time evolves, there is a transition happening, and we modeled it as an instantaneous transition, kind of a sudden transition in the equation of state. So we said the equation of state goes from -1 to some positive value, larger or equal a third. And this transition, we said, happens along a spatial surface, and this is the surface I'm drawing here in this space-time diagram. And since we didn't want to commit to a particular model at that point, we just said, okay, there needs to be a physical agent that makes this transition happening. And we call that agent Q. And once this agent or trigger reaches a certain threshold value, this defines the surface. So Q is some function of time and space. And now this transition surface is defined as the surface where this function takes on a particular threshold value. So Q might be smaller than Q star before the transition and larger than Q star after the transition. And by just making this simple assumption of having this matching surface, we were able to match the perturbation theory from before the transition to after the transition. And we found that, we found this matching relation, which tells us that the perturbations in the fluid after the transition, in the decaying fluid, are sourced by perturbations in this trigger, whatever it is physically. And what I want to talk about today is a particular model. I mean, there are different models that implement that idea, but I want to talk about a particular model where we give physical meaning to this Q, to make this more concrete. So today we are going to talk about vacuum phase transitions. So I will argue that this red line, in a particular sense, could be a phase transition. And this is then part of this new early dark energy framework, because we will see that again we need a trigger, and we can map it at the end to this picture. And the work I'm going, so what I've done up until now in the lecture is very general, right? We talked about the lambda CDM model, cosmological perturbation theory, the cosmic tensions, and how to think about them in general. But today I want to focus a little bit more on the work I have been doing with my collaborators, and most notably with Martin Slot from the University of Southern Denmark. And there we came up with a particular idea for how to set this up. So the motivation is that phase transitions are quite common in physics. So in cosmology, we for example, have the QCD phase transition. We have the electroweak phase transition. QCD, electroweak phase transition. So it's an idea which is rooted in relatively well understood physics. And to make the point why I think it's interesting with respect to the idea of early dark energy, let me start with a toy model. The toy model is a simple scalar field, which we are going to call psi. It's maybe a little bit of an unusual notation for a scalar field, but we need phi for another scalar field later. And this scalar field has a non-trivial potential. It's a non-trivial vacuum structure. So it has two minima that are separated by a potential barrier. And one minimum is a false minimum, and the other one is the true minimum. And the idea now is, in very general terms, that initially the field is stuck in the false minimum of the potential. And then you can identify the potential energy of that field. I mean, if it's at rest, I mean, if it doesn't have kinetic energy, it only has potential energy, then you know it behaves, if a field doesn't move and sits stationary in its potential, then it behaves like dark energy, or in this case, early dark energy. So the idea is that the difference between the false and the true minimum is what we are going to identify with early dark energy, or the value of early dark energy before it starts to dilute during that constant phase. But then the idea is that eventually the field tunnels to the true minimum. And this tunneling in position space you can understand. So let's draw the position space picture. You can understand as or manifests itself as the nucleation of bubbles of true vacuum. So what you get is a bubble, and yeah, if that's the color for outside, where outside the bubble you are still in the false vacuum, but inside the bubble you have already entered the true vacuum here. And there is an interpolating region which corresponds to this barrier, which is called the bubble wall. So this would be the wall. And what is interesting about these bubbles. So in our case, in this toy model, we look at the simplest case where this bubble nucleation happens at 0 temperature in some decoupled sector. So in other words, it happens in the dark sector. The field tunnels. This vacuum bubble comes into existence, and we can write down an energy balance equation, because you might wonder what happens with that energy that is released when the field tunnels from here to here. energy conservation must be satisfied. So there is a certain amount of released potential energy, which is simply the difference in the potential height times the volume of the bubble at initial time when it's being nucleated. And that energy goes into gradient energy in this bubble wall. So this wall, we can, at least in the thin wall limit, when it's thin compared to the overall size of the bubble, we can describe it as a tension. So this is the wall tension. And this has to balance the released energy from lowering the vacuum. And this scales like the volume. Sorry, the surface of the bubble. So this happens right after tunneling. You have a bubble. The wall of the bubble is at rest. But now you can see already from this equation that this is not going to be a stable configuration, because there's one term that scales like volume and another term that scales like the surface area. So by further increasing the bubble, you can release more and more vacuum energy, false vacuum energy. Of course, you also increase the surface area of the bubble wall, but that only grows quadratically, whereas the energy you release grows with the third power. So what you find is that very quickly, R dot, so the capital R denotes the radius of the bubble, R dot goes to 1, or to the speed of light. So we are left with vacuum bubbles that effectively expand with the speed of light. And if these nucleations are going to happen at different points in space, and all these bubbles are going to expand, I mean, they are nucleated at slightly different times, so some might be small, some might be large, but they are going to fill all of space. So this is what we call percolation. And eventually they are going to meet and collide. Okay, so, and then as I said, the overall idea is to identify what we call FEDE with the released energy in these phase transitions, or in these bubble nucleation events. So that's the idea. But let's look at the details. So the important parameter in this whole process is the tunneling probability. Which we denote as capital gamma. And well, I'm not going to go into the details of how to calculate capital gamma. There's a very nice seminal paper by Coleman. I think the reference should be in the notes, where this is done. Essentially what you do, you have all in your quantum mechanics lectures, you have all done sub-barrier tunneling for simple quantum mechanics problem. What you do, you need to generalize that calculation to the field theory case. And that allows you to calculate this tunneling rate. And what you are going to find is that it's going to scale like some characteristic mass scale of that potential. Think about it as the curvature of that potential, times by the Euclidean action squared divided by 2 pi squared to the power of minus the Euclidean action. And the Euclidean action is, well, the action of the theory evaluated in Euclidean time for a particular configuration that represents this tunneling. But that's for us, this is a detail we don't need to be too concerned about right now. What is important for us is that there is a tunneling probability to go from here to here, which in general is a finite quantity. And for potential like that, it's just a number. It carries dimensions. I mean, it's a space-time probability, so it's a probability per space and time, and you can calculate it for a given potential, and it's going to be a constant in that case. So that's important for us. So let's work out the probabilistic character of these nucleations. So the probability of a random point in space being in the false vacuum. So we are asking if I choose any point in space, what is the probability that this process hasn't happened yet? So that I'm not yet inside such a bubble. In false vacuum, that we can write as an exponential of minus I of t, where this I of t is the expected number of tunneling events in the past light cone. So it's very much like if you have particle decay, then the probability that the particle hasn't decayed yet has also exactly this exponential dependence where you would have minus t divided by the lifetime of the particle. And this is kind of the direct generalization of this in past light cone. So let's draw a picture to make clear how that works. So again, we have conformal time and space. And now we are asking, so we choose let's choose a point somewhere. Okay, let's do it a little differently. Let's say this is this is time eta, and there is an initial surface, could be the hot Big Bang. And now we are asking, what is the probability of this point, that something in the past light cone of this point, that there has been a nucleation event. So why is that a sensible question? So let's draw the past light cone. That's why I like conformal coordinates, because then the past light cone is just a straight line, because light propagates on curves or straight lines of 45 degrees. And now we can look at the tunneling event. Imagine that somewhere in this light cone, past light cone, there was such a bubble nucleation. What this means is that there has been an initial bubble. We can neglect its initial size because it quickly grows at the speed of light, so you don't have to worry about its size. But as it grows with the speed of light, or expands with the speed of light, we can draw it like that. So these are the extent. Think about it as the spatial extent of the bubble as it expands. And you will see, if that happens somewhere in the past light cone, just by looking at this geometrically, we always end up in the true vacuum here. This is why this is the right object to calculate. So if a nucleation has happened at any point in the past light cone, since bubbles expand with the speed of light, we are going to find ourselves in the true vacuum. And then the probability of being still in the false vacuum is the exponential of minus that number. So the higher the number is, so the more likely it is that such an event has happened, the less likely it becomes that we are still in the false vacuum. And of course, then the probability of being in the true vacuum would be 1 minus p. Okay, so let's calculate this number, I of t. And for that, we have to simply integrate over the past light cone. So let's do that. So and now I use physical time. And the reason is that the tunneling rate is a rate which measures the probability per physical time and proper space, so to say. So what we find is this. We take the tunneling probability, and now we have to multiply it by volume. So we integrate it over time and multiply it by the volume that corresponds to each time slice. So we have to, each of these slices represent a three-dimensional volume. And that is just going to be eta minus eta at time t minus eta at time tilde to the power 3 times by a cubed to convert it into a physical distance scale. So this is just eta t minus eta t twiddle is just this distance at each eta slice. So the spatial extent of the bubble at each eta slice. Okay, now we can use a few familiar relations. So we know that, okay, let's look at that combination, A times eta minus eta twiddle. So first of all, we can use that, let's assume we are during radiation domination. So then we can write the conformal Hubble parameter as, if we can replace eta with the Hubble parameter in that way. So what we get is that this is going to be Hubble to the power minus 1 at time t minus Hubble to the power minus 1 at t twiddle. And then we can use that Hubble during radiation domination. I mean, now the physical Hubble parameter is 1 over 2 times t. And then we get that this is t minus t twiddle. Okay. And this we can substitute back in here. So what we get is the integration. Okay, we get this constant factor. We can pull the gamma outside because it's a constant. We get the t integration of that expression. 2 times t, so it's to the power 3, so it's 8, t minus t twiddle cubed. Okay, and this you can just easily do. And what you get is 8 pi gamma divided by 3 times t to the power 4. And that we can rewrite again in terms of Hubble, using that Hubble is 1 over 2t. So this is going to be pi over 6 gamma h minus 4. Okay, and now the Now what we see is that at early times, when the Hubble parameter is very large, this I is suppressed, and the probability of us being in the false vacuum is very high. So at early times, nothing is happening. Only if the age of the universe becomes of the order of the lifetime of that false vacuum, do we start to effectively convert space into the true vacuum. So the condition for tunneling, so for the moment of the phase transition, is conventionally defined as the moment where this function I of t, so let's call that moment t star, is 1. That's the condition. And that condition is going to tell you that tunneling happens when the tunneling rate per volume is of the order of the Hubble parameter to the power of 4. And that defines the time of tunneling. Okay, so now we can right away estimate an important number, because I mentioned that this tunneling rate exponentially depends on what we call this Euclidean action. So one can calculate what this Euclidean action is for if we want the tunneling to become efficient at, let's say, matter radiation equality or shortly before matter radiation equality. So one important number here is that the Hubble parameter around matter radiation equality is 10 to the minus 27 eV. So this sets the scale of this tunneling rate we need if we want that phase transition to happen around matter radiation equality. Well, it's sufficient to have one tunneling event in the past light cone to convert the space. But in principle, there could be several events happening in the past light cone. Of course, you could have another one here, and they would have collided already before we reach the point where we are. No, that discussion is only kind of, well, it depends on the order of, it depends on the order of the phase transition, because only in a first order phase transition you get these bubbles. So only in that case it makes sense to draw these diagrams, because then you have a notion of a wall that expands. So we are talking about these strong first order phase transitions, which you always have in these vacuum phase transition cases. So it's different from the electroweak phase transition you might be familiar with. You, at least if you don't assume additional physics, there you have you don't have a first order phase transition. So there the story is different. But we are going to arrive at a certain problem related to that. So let me come to that. So okay. But as a quick side comment, I mean, how it works now is that tunneling becomes efficient when this parameter is of order of Hubble to the power of 4. And we said it's a constant in our case. So once you write down your theory, you decide on what that value is by choosing certain parameters in your potential and the overall scale. Then you have fixed the time when tunneling becomes efficient. And that was historically a problem for inflation, because the initial idea with inflation was to end it exactly like that, to tunnel from a false to a true minimum. This is what is called old inflation. But as you know, during inflation, Hubble doesn't change. So then, if initially the tunneling rate is smaller than Hubble, it always is smaller than Hubble if Hubble doesn't change. So this is called the graceful exit problem of old inflation. So you cannot use that process to end inflation. That's why people started to look at these crossover models. But in our case, it's different because we are not in a de Sitter. For us, this vacuum energy is subdominant. We are still during radiation domination, so our Hubble evolves. So even though initially gamma is relatively small compared to Hubble, Hubble drops, and eventually this condition is satisfied. That's just a side remark. But now an important quantity, there is now the duration of the phase transition. So how long does it take to convert all of space into the true vacuum? So what is the time scale related to that process? And this is conventionally denoted as beta to the power -1. So beta is an inverse time scale, and beta is defined as minus the probability, time derivative of the probability divided, or minus the relative change in the probability at tunneling time. And that, if you use the formula from before, is just the time derivative of this quantity I that we calculated here at the transition rate. So this gives you an idea of how quickly this happens. So if you think about a simple particle decay, this would give you the lifetime of the particle. But here it's kind of a generalized notion again. And let's calculate beta. So what we see is that beta, in our case, is going to be the time derivative of this quantity. Then you use again that Hubble is 1 divided by 2t, but you have an inverse power. So this goes like t to the power 4. Yes, and then you find that the beta parameter is 4/3 times pi times h star to the power -3. And then we can use that we are at the time of the tunneling event where also this condition holds. So let's replace gamma. And gamma is proportional to h to the power 4, but if you're careful about the numbers, you are going to get that result, h star. So the time scale on which this percolation is happening is set by the Hubble time at that scale, which is not surprising because everything is set in motion when the tunneling parameters of order of Hubble, but that is the only dimensionful parameter in the problem. Then it's not surprising that the time scale is also set by the Hubble parameter at that time. But this now, if we want to think about that false vacuum energy as early dark energy, and we want it to decay relatively late in the expansion history around matter radiation equality, is a problem. Because the duration of the phase transition gives you the typical size of the bubbles. And the reason is exactly that picture. If all the nucleation events happen within this time scale, beta to the power -1, this also sets their size because they can only grow up until the point where they collide. And since they all expand with the speed of light, they are not going to grow bigger than this parameter. So beta to the power -1 also corresponds to the size of the bubbles at the time when they collide. So this is going to be a characteristic length scale in the problem. So you get these colliding bubbles, and this is going to be a complicated a condensate of highly anisotropic condensate of fragments of bubble walls interacting with each other. But there is going to be this characteristic length scale. And that's a problem for cosmology because there are large inhomogeneities associated to that. So what we get are large inhomogeneities at a scale which is k times a h star. So this is just, the scale is set by the time when the tunneling happens. And now the problem is that if you look at the density contrast, you are going to find that, so what are these perturbations divided by the background? So what we have seen is that the background changes by delta V, that's the change in vacuum energy. So this is of order of delta V, but the inhomogeneities are going to be set by these bubble wall fragments, and they store all the energy from that has been released. So this is going to be something of order 1. So suddenly we introduce large inhomogeneities at relatively large scales. And remember, I said we can only address the Hubble tension if things happen in a relatively narrow redshift window between recombination and maybe redshift of 25,000. And this is entirely within the CMB epoch. And now we are exactly hit by the problem I mentioned before, that this is a highly constrained epoch in cosmology. And now we are suddenly introducing large inhomogeneities at observable scales. These scales are observable in the CMB. And that's a problem for the CMB. Simply speaking, we don't see bubbles in the sky. Okay. So we have to think about the resolution. And the resolution is to make this tunneling rate time dependent. Oops. So in other words, we want a mechanism that turns on the tunneling for us, and it turns it on very abruptly, rather than this very slow turn on where bubbles might have nucleated at any point from the past until today. We want to be in a situation where this happens more abruptly. So in other words, there are no tunnelings down here because it's highly suppressed, and it only starts happening very close to us. So these bubbles cannot have grown big. That would be a situation more like that. Okay. So let's do that. So the overall idea is to look again at the potential. But now that potential is time dependent, I'm going to explain how to introduce the time dependence of that potential. But initially, it's going to look like that. Our field sits here. And there clearly is no tunneling because you cannot tunnel upwards. Well, at least not easily. This is initial time. So we have block tunneling. But then the potential changes its shape. So the potential barrier shrinks. At some point, there are two minima that are degenerate. But eventually, we are in a situation where, well, let's draw it as a solid line, where we have clearly a true minimum, and suddenly tunneling can happen. So here we have enhanced tunneling. And yeah, let me write down what I So the resolution is to make the tunneling time dependent, and we want to do it in such a way that the derivative of the tunneling rate is much larger than the Hubble parameter at the time when the tunneling happens. So in other words, the time scale of tunneling should be short compared to cosmological scales. So then we can again calculate the beta parameter, which again is the time derivative of this quantity. But this quantity depends also on the constant tunneling rate. So it didn't, on the tunneling rate, it was constant before, so it didn't play a role for calculating beta. But now it's time dependent, and we have to take into account that time dependence. So beta is I dot at the moment of tunneling, and that is then pi over 6 divided by h to the power 4, sorry. And I can neglect the term where the derivative hits h, because we said the time derivative is much larger than h at that time. And then we can use the percolation condition, which was that condition again, to eliminate the dependence on h. And what we get is that this is going to be gamma dot divided by gamma. So the inverse duration of the phase transition is set by the relative change in the tunneling rate, which is controlled by this mechanism which lowers the potential. That's the idea we are looking at. And that is going to be much larger than h to the power 4, which means that the duration of the phase transition is very short. So bubbles don't get time to grow big. So there's no, tunneling is blocked all the time as we move forward in time, but only very close to a particular time where the tunneling is supposed to be happening. I mean, this I is going to be 1. Things turn on very abruptly, and these bubbles come into existence almost everywhere simultaneously and never grow big. Okay, so this is the idea. Let's write down the model that is supposed to achieve that. So this is the model we call cold new early dark energy because it happens at 0 temperature. That's why we call it cold. And what we look at is a two-field model. So we have a tunneling field, which we again call psi, and which has a mass scale, capital M, of order of the EV scale. So you're probably not surprised to see that, because the EV scale, as we've seen now many times, is the energy scale of the cosmic fluid around matter radiation equality. So that's the energy injection we need. But now we introduce what we call a trigger field. Little phi, and that has a mass little m, which is of the order of the Hubble parameter at that time. And I mentioned before, this is 10 to the minus 27 eV. So there's a huge hierarchy in scales between the trigger and the actual tunneling field. And the potential is a two-field potential. So we have a mass term for the trigger, but then we need this non-trivial vacuum structure. So we also need a cubic term, alpha over 3. And everything is controlled by this scale, capital M. That sets the scale of the trigger, the tunneling field. Psi cubed plus, that's, yeah. So sorry, that's phi squared, and then we have plus, wait a second, squared, no, that's cubed, plus and some quartic term, psi to the power of 4. And now the important part, so this is just, this could describe the potential I showed you before. I just erased it. So you have a cubic term with a negative sign and a quartic term. So for very large values of psi, we go positive again. But for intermediate values, we create this barrier because there's a minus sign here for positive EFT coefficients. But now we introduce an interaction with another field, our trigger field, lambda tilde, which goes like psi squared, phi squared, and then the trigger itself has a standard mass term. So this is a renormalizable potential. And it comes with these two mass scales and the coupling between two fields. And you see the trigger effectively acts like a mass correction to the tunneling field. So if phi is constant, then this phi acts like a mass. So now let's introduce a parameter which I call delta effective, which I define as some delta 0 and then 1 plus lambda tilde phi squared divided by capital M squared. And delta naught is going to be 9 lambda over alpha squared. And that has to be smaller than 2. I impose that condition. So these are the EFT coefficients that control dimension. They are dimensionless. They control the shape of the potential. We don't assume any hierarchies in them. They should be order 1. And what we get then, or find, is that this delta parameter controls the shape of the potential. So we can draw the potential in the following way. So if delta is effective is very large initially, then we just have one minimum and that's it. And you see, how do we achieve that delta effective is very large? We need phi to be sufficiently large. So this is the first stage. So first, initially, the Hubble parameter is much larger than M. That is then you know what happens if the Hubble parameter is much larger than M. Then the trigger field is going to be frozen. So phi is frozen, and then we demand that delta effective is larger than 2, which translates into a condition on the initial value of phi just by using this relation. So this has to be larger than 2 alpha squared divided by 9 lambda twiddle. Okay, and in that case, since there is no second minimum to tunnel to, we have blocked tunneling. So nothing is happening in the early universe. But then at some point, h becomes of order of the mass. So we say somewhere close to matter radiation equality. That's why we say m is of order of 10 to the minus 27 eV. That's our clock, so to say, that decides when everything starts. Then what happens is that phi evolves. And as phi evolves, let me see. So phi, the potential of phi is just a quadratic potential. So it's initially frozen somewhere high up, and then it starts rolling down. So phi decreases phi decreases, and if phi decreases, also delta effective decreases. So we are still in the phase where it just starts rolling. That hasn't started to oscillate yet. And what happens to our potential is that it changes its shape. So it then develops a second minimum. And simply because this interaction term has a stabilizing effect for the false minimum, but as phi goes down, the effect of this interaction term subsides. And finally, we are left with a situation where there is a true minimum down here, and tunneling can happen. So this would be the third stage. The third stage is at least reached when the field reaches the minimum, because then this interaction term goes away entirely, and then the tunneling rate is maximal. So what we find is that for H, that you can do analytically, you can calculate that number is 0.18 times the mass. Then phi is vanishing, and delta effective is delta 0, and then you have the maximal tunneling rate. And you can show, I'm not, because I'm again running a little low on time, it's calculated in the notes, it's not hard, but it's, what you find is that the maximum tunneling rate, so we start out from a situation where tunneling is much, much smaller than 1, so it's effectively blocked, and end up in a situation where it's 10 to the power 108 times a suppressing potential, exponential, delta 0. So this huge number comes from the fact that there is a huge hierarchy between scales. So I mentioned to you before that in this model we have this hierarchy between the EV scale and the Hubble scale. So the reason for that is that we are very late in the expansion history. Late in the expansion history, the Hubble scale as an energy scale is much, much lower than the scale of the energy density in the plasma. And so we have this hierarchy, but capital M determines the scale of the tunneling rate. And for here you divide the tunneling rate by Hubble. So this gives you this huge number. But there is a suppression from this Euclidean action story. I'm not going to talk about that much. But you see that as long as lambda is larger than roughly 0.1 times delta 0, this is still a very large number. This is much larger than 1. So you have started in a situation where the tunneling rate was much smaller than 1, and you have ended up in a situation where the tunneling rate is divided by Hubble, is much, much larger than 1. But we have just before learned that tunneling becomes efficient when the tunneling rate is in units of Hubble is of order 1. That means that tunneling must have happened somewhere in between these two extremes, just by continuity. You scan many orders of magnitude in the tunneling rate, so somewhere in between the tunneling must have been efficient enough to convert the space on a very short time scale. Okay, so let's draw the more intuitive picture. There are additional calculations in my notes, but let's not calculating this beta parameter and so on precisely. But that should give you an idea that by doing that, we can turn on the tunneling on a time scale that is suitable to the problem we're looking at. So this is the picture then. We have this transition surface. And now here we are in the false minimum. So the equation of state is -1. And there's this critical value. This was the lesson from here. So there is going to be a critical value. Phi equals phi star, where the tunneling is of order 1 in units of Hubble. And once this value is reached, phi star, so here we are larger than phi star, so we are higher up in the potential, and here we are smaller than phi star, then all the bubbles are being nucleated, so we can draw their trajectories, but they are nucleated very quickly, so it's kind of, they collide very quickly, and we are left with a complicated condensate of these colliding bubbles after the transition. So this is the picture. So in other words, in the language of this effective description, you have identified Q as a function of eta and x with this, what we call the trigger field now. So it's the same idea, but what is important is that there are perturbations related to perturbations in the trigger field, and these are perturbations on cosmological scales. I mean, these are small k modes, so to speak. And then there are these tiny perturbations related to these tiny bubbles. They are microscopically small. They never grow big. And these perturbations correspond to large values of delta, but only for extremely large k modes. So the small k modes are set by perturbations in the trigger, exactly as we described it yesterday. But there's this small scale condensate of inhomogeneities and anisotropies related to this colliding bubble condensate. Okay, so in the notes, I'm going to talk more about the radiative stability of this potential, because whenever you have a potential with two very different mass scales, you have to worry about quantum corrections. So the light mass receives corrections from the heavy mass particle, and in order to stabilize this, you need to impose a bound on lambda tilde. So that you find in the notes, and I also, in the notes, we talk about a way of embedding this in an axion framework, because that can give you a more natural explanation of the smallness of the scale, but a more conventional axion framework, not the one in AXI-EDE where you need to pick a certain power of the cosine. Here you can start with the leading order, so n equals 1, and get something like this in the two-axion model. Okay, but let me now talk about the post-phase transition. Okay. So after the phase transition has happened, you have these bubbles, they expand and quickly collide with each other. And this is now a quite complicated process, because there are different things going on, and it becomes very model dependent. But in general terms, there's always going to be a gravity channel, because you have these bubbles when they collide. A single bubble that expands doesn't emit gravitational waves because it's spherically symmetric. It doesn't have a quadrupole moment. But once they collide, they develop quadrupole moment, higher moments, so they are highly anisotropic. And so they create anisotropic stress, and that sources gravitational waves, so tensor shear, which is just a different word for tensor perturbations, gravitational waves. And gravitational waves, they then form a stochastic background of gravitational waves. So it's not like a merger event. You can identify a single gravitational waves. Here you have many bubbles colliding, or you can think about in the position pictures, you have all these bubbles, different sizes, they come into existence, expand, and eventually they collide, and that is going to form a highly inhomogeneous state. And that is going to lead to gravitational waves, tensor shear. And gravitational waves are, if you average over them, because this happens on small scales, we are interested in cosmological scales, then you're going to see that they behave like a fluid with an equation of state of 1/3, because they are radiation. But there's also vector shear and scalar shear, which are the modes. So what if you decompose the energy momentum tensor, there's a component pi ij, which is the anisotropic stress, and it's the traceless spatial component of the energy momentum tensor, plus components that are proportional to ij. These would be the pressure components, but this anisotropic stress can be decomposed into a tensor, vector, and scalar part. And the tensor part sources gravitational waves. The vector part is going to source vector shear, and the scalar part is going to source scalar shear. And they behave like a stiff fluid on large scales. So you get something which is a mixture of radiation and a stiff fluid. But then you can have additional microscopic channels. So that then depends on the model. So you can introduce Yukawa couplings. You can have a coupling between psi and some fermion chi, say, and then you decay into these states. And then the physics of this chi sector determines how this fluid behaves. So this would be similar to reheating after inflation. But that's up to you if you include these channels. But the message here is that whatever happens after the phase transition, you have these wall fragments, but eventually they dissipate into different channels. And if you zoom out, there is no preferred direction or position in this problem. So you can, again, apply a fluid description. And the idea is to apply the NEDE PHENO model. So NEDE stands for New Early Dark Energy. PHENO model I discussed yesterday. But now you can relate some of the parameters with the parameters of the fundamental theory. So what we called FNEDE, FEDE, I think. I wrote it down before. It's just the difference in vacuum energy. We can express that in terms of the model parameters, and it's going to be 1/10 into alpha 4 divided by lambda cubed, m to the power 4 divided by m Planck squared, h star when the tunneling happens squared. And then you see that this is just the energy density of the cosmic fluid. And if m is of order EV, you get a 10% energy injection for order 1 coefficients of the potential. So this is alpha. So now we are in a situation where we can map the parameters of this more fundamental theory to this effective fluid description we came up with yesterday. That's the idea. But this dictionary, I mean, is still very much work in progress, because we can relate, what we can relate is to the fundamental parameters is this F parameter, and we can relate the redshift when it happens. That is controlled by the mass of the trigger field. What is more difficult to achieve is getting this effective equation of state of the decaying fluid, because these are complicated things to calculate, how this bubble wall condensate sources gravitational waves. So for that we use an effective fluid, I mean, we still use this effective equation of state parameter. So what we still do, simplifying assumption, that that the equation of state characterizing this post-phase transition fluid, well, can be described as a constant part plus corrections, which are small. And recently we tested this assumption by including the first set of corrections, and we found that this is justified. But ultimately, of course, what we'd like to do is relate this parameter to the fundamental parameters of the theory, like the EFT coefficients here. So this is something that is difficult in this model. Then what is interesting, and let me just mention it, that there is now this trigger field, and it just runs down a quadratic potential. So this goes like phi squared. So as we have seen yesterday, having a scalar field that oscillates around the minimum of its potential behaves like dark matter, certain type of dark matter. So in this model, by triggering the phase transition, we also quite naturally make a contribution to dark matter. We are not going to explain all of dark matter. It's a small contribution, but it turns out to be actually good that it's a small contribution, because as I said, it's a very special type of dark matter. It's called fuzzy dark matter. It has different properties than cold dark matter, simply because it's a scalar field. So its perturbations behave different. Only at background level it does behave like like standard dark matter, but on perturbation level it behaves differently, and it has the property of suppressing the matter power spectrum, because it has the perturbations come with a positive pressure. So this is interesting with respect to the S8 tension. I just wanted to mention it, but you can work out how much dark matter you get. So what you find is that omega phi, so the abundance today of that field, is controlled by the redshift of the decay. So let's say it happens, let's normalize it with respect to 5,000, which is roughly the time when all of that happens, times by this factor times by phi initial divided by m Planck. So in other words, it's controlled mainly by the initial field value of this trigger field. So if the trigger field starts out very close to the Planck scale, but still below the Planck scale, we get a small contribution to dark matter. So remember, dark matter is cold dark matter in the lambda CDM model is 0.25, and we can get for, let's say, phi ini is one order of magnitude below the Planck scale, then we actually, I think, let me see if I did the normalization right. So now I wonder, I remember it to be even smaller, but in any case, if phi is close to the Planck scale, you see that you can get a small contribution to dark matter. And that is interesting with respect to the S8 tension. So that suppresses S8 slightly. But you can control it by choosing the value of phi initial. If you make phi initial smaller, then this contribution goes down. So you have some control over that effect. And do I still have the expression for delta effective? Yes, because there, you see, here we also have another bound on phi initial. There's also a lower bound. And the reason for that is that we want the field initially to sit high up in its potential to suppress tunneling. If you start too low, then it's not doing anything. So you have to make sure that this bound doesn't contradict, I mean, satisfying that bound shouldn't overproduce dark matter on that side. And you can make that sure. So what you, let me see, did I do that? Yeah, so what you find is that if you demand that delta effective is larger than 2 initially, which we needed, then you find that phi initial is larger than 2m squared divided by delta 0 lambda twiddle. And that we can estimate as an order 1 number for delta 0 times by 10 minus 3. I keep that just a second. Delta 0 minus 1. Then I substitute in a bound on lambda tilde, which makes sure that the potential is radiatively stable. But let me just state the result because I didn't have time to derive that. So we find that there's a lower bound, which is that this has to be 10 to the minus 3 in units of m Planck to the power 2. So in other words, yeah, and that's phi ini squared. Okay, so now it makes dimensionally sense. So in other words, phi initial has to be larger than 10 to the minus 3 m Planck, but it has to remain sub-Planckian because otherwise you run into problems with well, corrections from quantum gravity, simply speaking. You don't know what's going on above the Planck scale. So there is a window where you can live between 10 to the minus 3 m Planck and m Planck. And this window turns out to be exactly interesting for getting a sizable contribution of this type of dark matter, fuzzy dark matter. So this is something interesting in this model. But now, finally, let me show you what happens if you use this phenomenological model and test it against data. So what we did is we implemented that idea into a Boltzmann code, into class, and what we did technically is very close to what we did yesterday, kind of this decaying fluid. But this time we made the choice that the trigger is a slowly rolling scalar field. So you describe in the code a slowly rolling scalar field with adiabatic perturbations. And these adiabatic perturbations are the perturbations that get imprinted in this decaying early dark energy fluid. And so there's the Boltzmann code. It's called trigger class. And it takes different input parameters, the time when the decay happens, that is related to the mass of the trigger field, as we have seen. It takes the amount of early dark energy. That, as we have seen, is related to the mass of this tunneling field. And it uses this decaying fluid equation of state. It takes this as input parameter. And then you have the choice of either saying this is highly subdominant, then you don't need to specify it, or you can allow for a sizable amount of this omega phi. So you have a 4-parameter extension of lambda CDM, and that you can test against data. And then what you find is that what these models do, and this is very similar to AXI-EDE. I mean, at this level, in the phenomenological level, these models have differences, but overall they behave very similar. So if you look at the H0, FEDE plot, then you see, and you run Planck 2018, BAO, and Pantheon data, kind of standard BAO data, Pantheon data, then you find that the effect of this model is that it introduces an approximate degeneracy in this plane. So it's going to look something like that. So the more FNEDE you have, the higher H0 gets. This is how we set up this model. But the interesting thing is you can get relatively high values. So the shoes constraint would live somewhere here. So you can see kind of the precise plots. I put some of them in the notes and references to the paper. So there you get the nicer plots. But this would be the shoes constraint. So the local measurement from the distance ladder. And you see that you overlap with it, which is good. And then you can break that. So this allows you to combine with this measurement, and then you break this degeneracy, and then you know you have to live here. And such a plot looks very similar for both models, new early dark energy and AXI-EDE. So in a way, they are very similar. And the hope, of course, is that more precise CMB and supernova data in future are going to discriminate between these different microphysical ideas. I mean, in one case, one has this scalar field that oscillates in an anharmonic potential. And here we have this vacuum phase transition with all these bubbles being nucleated. But yeah, let me finally mention what some of the open issues are and what's currently going on. So I thought that might be interesting. So this was the picture maybe a year ago. Kind of these standard data sets give you this picture which reduces the tension. I think for these data sets we found that the H0 tension goes down from 5 sigma to 1.4 sigma. But now new data sets have come up. And what we find with new data sets, so if you replace this by Pantheon, so Pantheon by Pantheon Plus, if you're familiar with these things, and Planck by NPipe, which is using the same data, but in a reprocessed way. They try to get more out of that data. So it's maybe still a little bit the question what the status of this NPipe is. But then we checked for this data. We did it for both AXI-EDE and our model. And in both cases, both models, I mean, first of all, you find that with these data sets, the initial tension increases more to the 6 sigma level. But both models become less efficient at addressing it. So you go down to the 3.5 sigma level. So it's still an improvement, but suddenly you see you're not fully resolving it anymore. And this is in a way what you expect. I mean, as data becomes more and more precise, we also have to be more and more precise about the model building and have to learn from data what it tells us and yeah, keep exploring. And I thought this is maybe a good note to end this lecture by saying, I mean, this is one idea, an example of an idea. I'm excited about that still because it gives still there's a lot to be explored and to be generalized. I mean, this equation of state needs to be understood. These corrections, we have included them recently, but there are more corrections also to the sound speed and so on. I mean, we make different assumptions and they need to be understood. But overall, data becomes more constraining, and we are certainly not at a point where anyone can claim to have the solution to the Hubble tension. So I would say right now there is no full generally accepted solution to it. So there is still a lot of work to be done in this field, and yeah, let me end on this yeah, somewhat hopefully optimistic outlook. Thank you. Oh yeah. So fuzzy dark matter. Yeah. So what is happening with fuzzy dark matter is that you have the scalar field that oscillates around the minimum of its potential, and then if you look at the perturbations, you find that in some range, so for small K modes, they oscillate too, but coherently with the background. So they are not associated with, they behave very much like the background. So they are not contributing a pressure. So they behave like cold dark matter perturbations. But for larger K modes, they're suddenly, they are out of phase compared to the background. And this effectively introduces a pressure. And this pressure then acts against gravitational collapse and changes predictions for structure formation. Yeah, that's maybe the short answer. Yeah. Yeah.
So you said that there are tensor perturbations.
Yeah.
Do we detect them, or are they different from the primordial tensor perturbations that are there?
Oh yeah. That's a very good question, of course. Yeah. So this is a stochastic background of gravitational waves, and we know that inflation also predicts a background of gravitational waves, which gets converted into B modes, which we are looking for in the CMB. But these things happen at very different scales, and the spectra are going to look very different. So this is going to lead to a gravitational wave signal, which is going to be peaked around the characteristic scale of this state of colliding bubbles. So these bubbles, when they collide, they have a certain characteristic size, which we called beta, inverse beta, right? That's their size, and this beta is going to set the typical frequency. And now we have set everything up in such a way that beta, this frequency, is not observable in the CMB because we wanted to avoid these large inhomogeneities. So the same applies for these gravitational waves. So even though, yes, you produce them, they wouldn't lead to a signal in the CMB. So that's the first thing. But in principle, you can ask about other gravitational wave experiments. So what you find in this model, if you calculate the gravitational wave signal, you see it might marginally overlap with the pulsar timing array if this beta is relatively large. So if you get close to to a bubble size where you might start to see them in the CMB. Then at the same time, you might have a signal impulsor timing arrays, but it's in that case very marginal. There is another model where the phase transition is hot NED, where we use temperature as a trigger, where everything happens earlier in the universe. Then the story is different. Then you can have gravitational waves you can look for. Yeah. Mm. Oh yeah. That's also a good point. In principle, you can have isocurvature perturbations in that model. We haven't really. That's one of the many things that one needs to explore in detail. I mean, right now we make the simplest assumption and say there are only adiabatic perturbations. But in principle, you're right. There could be isocurvature perturbations too. Yeah. Mm. Mm. Yeah. 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 So the story here is that once you have this colliding fluid condensate, you create all sorts of different gravitational modes. I mean, as I said, these scalar shear and vector shear modes, but they dissipate quickly. For us, that quick dissipation is an interesting feature because we want this early dark energy to dissipate quickly. But if you have something happening in the early universe, whatever redshifts as quickly as that with an equation of state of 1 is very quickly negligible. So for that reason, you wouldn't worry about these components. If they are non-zero, they are going to go away very quickly. Yeah. I mean, I'm not sure about JWST, but so what we are looking into is yeah. I mean, more like Lyman alpha data, and because you suppress S8 a little bit, but you also introduce deviations from the lambda CDM matter power spectrum at very small scales. Just because you have this particular fuzzy dark matter. And what I didn't say is this dark matter in our case is also predictive in a way because the mass is not a free parameter. I mean, it's highly constrained. It's going to be 10 to the minus 27 EV, which from the perspective of these fuzzy dark matter models is a relatively small mass. So this means that you have observable signatures in the power spectrum in an actually quite interesting range. So that's something to look into here. Yeah. Mm. Yeah. 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 Oh, yeah. That has a large error bar. So you say C star is typically 5,000 plus minus 1,000. So of that order. But if you translate it into an energy scale or the corresponding Hubble parameter, then this doesn't vary very much. I mean, this was one of the first exercises where we showed that even if you go to the start of the CMB epoch, which is a redshift of 10 to the 5, I mean, you are still in the range of EV scale physics. Because the reason is that rho scales with the redshift squared during radiation domination. So to get the energy scale, you take the fourth power. So it only scales with the root of the redshift. So that's, yeah, just means if you translate it into energy scales, this is a relatively robust statement.
There are no further questions. Let's thank Florian once again for this very nice.